This is the heart of the microwave oven, and it is essentially, it's called a magnetron, and essentially it consists of a vacuum chamber that contains a filament that's heated up by putting power on some two wires here to a point where it will emit electrons. And around this filament is an anode, which is connected to these fins, which takes away the heat that doesn't get used into making power. And this end here is the power output. This connects into the cavity, which is essentially the oven. The waveguide, we call the oven a cavity. So that's what the heart of a microwave oven is. This is the power generator. It's very high frequency. But basically, the tube itself is simple. And here is if you cut away all the outsides, you see what I've done here is taken away all the outsides. And we have, again, the connections to this hot filament I was talking about, and we have the connection to take the power out. And then your question is, well, how does it make power? So we took one of these apart, and you can see what's inside of it. I was telling you about a filament. This filament has broken, but there's usually a spiral of tungsten or thoriated alloy tungsten connecting between this point and this little shell here. And that's the thing I was talking about getting hot. And the electrons that are emitted by that filament, when you put voltage between that filament and this anode, would ordinarily just zing straight across and nothing would happen. But there's a magnet here. That's what this black thing is. It's a magnet. So when electrons start to move in one direction, the magnet turns them. And depending on the voltage, it turns faster or slower. So now we've got the electrons whirling around in a circle around this filament. And they're not going over to connect to this copper anode. Now you notice the anode isn't a solid piece of metal. It's got some veins. These are designed to be resonant at the frequency that we want. Resonance is like when you have a person on a swing and you want to make them go fast or higher. You push them at the right time, so that each time you push, it goes faster. Instead of hitting them when they come back at you, you're going to stop them. The electrons go by each of these veins at a time such that they can kick another electron that's inside this copper at the right time to start building up a voltage. And that's what happens in a magnetron. Electrons whirl around at the right speed to generate a wave energy in an anode, which is designed as a bunch of resonators. So now you've got this thing making microwaves, but you have to do something about getting the energy from there out. They go round and round at a speed such that they are essentially synchronous with the voltage, which is a high-frequency voltage that's changing rapidly back and forth, essentially like a synchronous engine or motor would be. They're generating electric fields, which are stored in these veins, between the veins, as electromagnetic energy. That's a resonant cavity. Now, how do we get that power to come out to put it in an oven so we can use it? There is a cap on the end here and an insulator, and a small rod from this cap connects to one of these little veins to connect the power out. And by mounting this probe in the side wall of the oven cavity, which you can see here, you mount that to the wall of the cavity and stick this inside essentially the oven. You radiate, essentially a radiator, energy into this oven. Now the oven itself is also a cavity, waves bouncing back and forth off all the walls. And if there's a piece of material in the cavity, like a food item, they impinge on the food. And in the process, the food absorbs the energy and gets hot. And because the wave is coming in from so many different directions, it heats all the way around, and it also penetrates into the food and makes it cook relatively uniformly inside as well as outside, unlike other ways of cooking, which essentially require the heat to come in from the surface and conduct it instead of going in as an electromagnetic wave. And the primary mechanism is you're heating the water content or the fat content of the food rather than heating the dry materials that might be the fiber materials. This is an older version of how you connect the microwave power into an oven. This is probably a vintage 1960s, so late 60s. This flange would connect to the wall of the oven through a hole. You would radiate the power into. Essentially, in the oven, there is a little thing called a waveguide, which gets energy from this probe. And the waveguide is essentially a square piece of tubing that goes down to a hole in the oven wall to radiate the food. In modern design, people have learned how to make joints out of materials, ceramics, which are low loss and stronger than glass. They don't break. But the same idea exists. This piece I'm holding here is the output end of a new oven, magnetron, and it has a big cap on the end. But the same idea. It sticks into a waveguide and radiates into the oven. So it shows the evolution of the design of magnetrons over some probably 20 years. You know, the advent of metal to ceramic joining, which people like Jim Baggs and Ralph Bonnelly pioneered, made a whole world of difference. It's mechanically stronger, it's electrically less lossy, and you can see it's just the way to go. This thing is so fragile, if you bump it, you're going to break it like a glass lamp bulb. So this is again, technology advances as time goes on.